Hello everyone, my name is Reinaldo Cobos and together with David Drescher and Jan Brunik, I'm happy to present our paper on power and energy communication services for control software models. I will begin giving a brief introduction on the context and motivation of this paper, followed by a theoretical framework on the constraints of energy exchange that we later put into meta models to describe the power communication services. Then I present you use cases using the power communication services, and finally conclusions and recommendations of this work. This work is in the context of energy-based control in robots. Why do we use energy-based control? Well, because we can achieve a robust and stable compliant behavior by using energy shaping techniques to not only control positions and forces, but basically to shape the complete physical interaction of the robot with the environment. When robots are working in unknown environments, it means that we lack information about the environment or we have incomplete models. Then having compliant behavior is safety essential. And by compliant behavior, I mean, for instance, being in a dark room, we use our arms to detect the environment in a way in which we don't hurt ourselves. So energy-based approach can achieve the compliant behavior, and this is convenient for safety. But when we are implementing energy-based controllers in software, this requires energy-consistent computation, configuration, and composition of the software. To do this right, the software must conform to the laws of energy exchange, so basically conforming to certain physical laws. This requires expertise on physics and physical system modeling, besides the expertise needed to compose and develop the software. So there is a need to describe communication in terms of energy exchange. Some physical system modeling tooling and some domain-specific languages support this feature, but still there is a need to extend this communication between controller algorithms, especially in the communication between software components and the communication between the software itself and the physical system to be controlled. So the contribution of our paper is defining meta models for communication services to adhere to these requirements of energy exchange. This is essential, otherwise the software can compromise the stability and safety of the entire robotic system. So in order to have energy consistent communication, we first have to identify the constraints of energy exchange. So how the energy is exchanged in the physical world. And for that, we define energy exchange as a flow of power. The flow of power among elements, for instance, the impedance controller and the physical system shown in the slide. The power is computed as a product of two signals, effort and flow. Effort corresponds to forces and flow corresponds to velocities in the mechanical domain. So the product of these two signals has its units in watt. These two signals have to be instantaneously communicated one to one, which means that we cannot simply split one of these signals and communicate another element and still describe this as a power exchange. This is not possible. Additionally, effort and flow signals must be collocated, which means that they correspond to the same reference frame or the same coordinate frame. And their computation is causal, which means that effort is a function of the flow and flow is a function of the effort. And this causality property determines inputs and outputs in the software. So effort and flow signals have to be computed in opposite directions, just as it's shown in the slide. So in summary, the constraints of energy exchange are applied to the communication of the two signals, effort and flow, and these signals must conform to causality, uh, being communicated one to one, with effort as input and flow as output, and the other way around. So these are the two causal arrangements. The signals have to be collocated, expressed in the same coordinate frame, and instantaneously communicated. However, if we are dealing with discrete systems, we cannot achieve such a thing as instantaneous communication. Instead, we can achieve synchronous communications. So the arrival of these signals have to respect deadlines, and for that we use real-time systems to guarantee the timeliness of this communication. Once we have identified these constraints, we proceed to describe them as communication services in meta models. For that, we have the power communication service meta model and the energy communication service meta model. However, for given the time, I only show the power communication service meta model, which is now in the slide. For this communication service, we have two causal arrangements, so effort as output and flow as input, and the other way around. And for each of the causal arrangements, we have the effort and flow signals or data streams with a collocation relation. So they have a collocation constraint, which means that they correspond to the same reference frame, and a timely relation. So the communication of these signals have to, or the arrival of these signals have to respect deadlines. Um, these signals, effort, and flow are defined as data streams, so we can guarantee the one-to-one communication. Once we have defined the meta model, we can proceed in the construction of models. For instance, this controller, which is shown as a UML diagram and a block diagram. The elements of this controller A, B, and C, they are related using the power computation communication service, and the causalities are also shown. These two models conform to each other and conform to the meta model, and all pairs of ports are collocated, timely related, and causal constrained. This way, A, B, and C are described as elements that can exchange power. We have defined a use case example consisting of a robotics system engaging in physical interaction, in which controller has certain requirements such as using energy-based Cartesian loop control, outputting forces while measuring positions in return, and using a passivity enforcing algorithm to guarantee the stability of the control system. So details of this passivity enforcing algorithm can be found on the paper. We can construct the models based on these requirements, and we can see that our models or elements in the models relate to each other through the power computation communication service, in which the forces and positions can be used to reliably compute power. And both diagrams conform to each other, so we can derive one from the other, and they also conform to the meta model. So basically we have two different views of exactly the same controller. It's just a matter of preference if you're using one description or the other, as long as they conform to the communication meta models. As conclusion to this work, we convey energy exchange to software models by representing them as meta models that guide implementation of the required constraints in software. By constructing models according to these meta models, we can bridge the gap between software engineering and the physics domain in the description and communication of power and energy. We recommend to use these meta models to assist on the development of software tools and standards, in the automated conversion and consistency check of models, and in the future leading to the automated construction, verification, and code generation. Future work will be focused on facilitating the energy-based approach in robot control software by enabling energy as a control software property. And to do this, we're going to embed the energy exchange in control architecture. And to do this, a first important step is to have a reliable description and communication of power and energy according to physical laws, and that is the motivation of this paper. This has been all for today, and thank you very much.